This is your video for section 7.4. In this section, we're starting to talk about vectors. Sometimes we talk about quantities that just involve magnitudes, things like 45 pounds or 60 miles per hour. These we can represent by just a single real number. We call these real numbers scalars. There are some other quantities that we call vector quantities that have both a magnitude and a direction. Some examples of these would be if we talk about velocity. Velocity has both a magnitude, which would be the speed, and it also has a direction. This would be something like 80 miles per hour west, so we've got both the magnitude and the direction. Or if we're talking about an object, it could be going 100 feet per second upward. So there we've got the magnitude of the velocity and also the direction. Some other vector quantities that we run into are acceleration and also forces. An example of a force that we talk about a lot is gravity. Gravity acts downward towards the earth. What we would think of as the magnitude would be the weight of the object. When we talk about vector quantities, we can represent these with a line segment, and this is a line segment that has an arrow on one end so that we know which direction it's going. This is called a vector. The length of the vector is going to be the magnitude of the vector quantity. Here's what a couple of vectors would look like drawn out. If we have two letters that say the beginning and ending of the vector, we could name the vector just by naming those 2 points. The first point is going to be the initial point of the vector. In other words, that's where it's starting. And the second point is going to be the terminal point or the end point of the vector. That's where it's ending, and that's going to be where the arrow is. So this vector right here would be OP. This vector right here, because it starts at P and ends at O, this one would be PO. If we want to write the magnitude of a vector like this, it's actually the length of that segment, but the way we write it is with vertical lines on either side. It looks like an absolute value symbol. For two vectors to be equal, they have to have the same direction and the same magnitude. Our two vectors here both have the same magnitude because the lengths are the same, but their directions are actually opposite of each other. So these two have the same magnitude but opposite directions. That means these two vectors are not equal to each other. If we're thinking of them as vectors, vector OP is not the same as vector PO. Another thing we can talk about if we have two vectors is the sum of the two vectors. When we add vectors, the addition is commutative, just like we're used to with real numbers. When we add two vectors A and B, this is called the resultant of the two vectors. Now when we're drawing this out, there are two ways to do it. This way here, we use this in a lot of the navigation problems. So if something starts from here and is going this direction for this long, and then at that point it turns and goes a different direction, then the resultant vector would be from the beginning of this vector to the end of this vector. So this vector right here, from here to here, would be A plus B, or the resultant vector. If we draw them this way, this is called the tail to tip method. That just means that we're putting the tail of one vector at the tip of the first vector. The other way we can do this is what we call the parallelogram method. This way is more useful if both of the vectors are starting from the same point. So here we have two vectors that are starting from the same point. If we want to know the resultant vector, the A plus B, what we can do is complete a parallelogram with the two vectors as two of the sides of the parallelogram. Remember with a parallelogram that sides opposite each other are the same magnitude, so we could actually redraw our vector B over here and redraw our vector A over here. That means that these two sides have the same length and these two sides of the parallelogram have the same length. Then our resultant vector is the diagonal of the parallelogram. If we have a vector u, then there's a vector minus u that has the same magnitude but the opposite direction. This is called just the opposite of the first vector. If we add u and its opposite, that vector has magnitude of 0, and we actually call it the 0 vector. Another thing we can do with vectors is multiply them by a scalar. This is called the scalar product. Remember, a scalar, when we're talking about these, is just a single real number. If we take a scalar times a vector, what we get is another vector. We get the magnitude of the new vector by multiplying the original magnitude by our scalar. If our scalar is a negative number, we use the absolute value of that. Our second vector is going to have the same direction as the original one. If the scalar was positive, it'll have the opposite direction if the scalar was negative. So here's some examples of that. If we start out with this vector u, this vector here would be 2 times u. That means it's going to go in the same direction, but the length of this is actually 2 times the length of this one. So the magnitude of this one would be double the magnitude of that one. Here's some other multiples of u. Notice all of these, since we're multiplying by a positive number, all of these have the same direction. They're all starting at this end and ending at this end. They do all have different magnitudes, but they all have the same directions. Now this one, this is negative 2 times u, so this one is actually going in the opposite direction. Notice it starts here and ends here. This one has the same magnitude as 2u, so this one and this one have the same magnitude, but they're opposites of each other, so they're going in opposite directions. Let's look at a couple different vectors. We're going to start out with vector u. We know that this has a magnitude of 3 and a direction angle of 15 degrees. Now for these, when we talk about a direction angle, that's typically going to mean the direction from the positive x-axis or the direction from the horizontal. So positive direction would be going counterclockwise. This has a direction angle of 15 degrees. This angle would be 15 degrees, and then our magnitude is 3. That means the length of this line segment from here to here is 3 units. If we want to find the magnitude and direction angle for the opposite of u is going to be a vector with the same magnitude, but it's going to be going in exactly the opposite direction. So we would just have something going in the opposite direction, but it would be the same length as that one. The magnitude would still be the distance from here to here, which would still be 3. To get the direction angle, what we just did was we took something that was exactly 180 degrees from our original vector. So if the direction angle for our original vector was 15 degrees, we just added on another 180 degrees. The direction angle for the opposite of u would be 15 degrees plus 180 degrees, which would give us 195 degrees. Now let's look at vector v. This one has a magnitude of 4 and a direction angle of 75 degrees. And this time we're trying to find the magnitude and direction for negative 2 times v. If we're considering that our direction angle is starting from the horizontal, then 75 degrees would be something like this. So let's say that our vector v ends right there, so that this distance from here to here is 4 units. If we're taking negative 2 times v, that means we're going to multiply the magnitude by 2. So that means our magnitude is going to be 8. And we can write this with the little absolute value symbols, so that would be 2 times our magnitude of 4. So that would be 8. That means in terms of drawing it, it's going to be twice as long as this one. And because of the negative, it's going to be going in the opposite direction. So that would be negative 2 times v, the magnitude would be 8. And then to get the direction, we're going to take our 75 degrees, and again, we just went around another 180 degrees. So we would take 75 degrees plus 180 degrees. That gives us 255 degrees for that direction. Now let's look at the resultant of u and v, which would be the same as the vector u plus v. So this time we're going to have to draw both u and v together. When we do this, it doesn't really matter which method we use. We can use the tail to tip, or we can use the parallelogram. For this one, I'm going to do the parallelogram. So that means I'm going to start both of the vectors at the same point. Now here's my initial point. So there's my vector u, and this angle right here is going to be 15 degrees. My vector v has a direction angle of 75 degrees, and the magnitude is 4. So this entire angle from here down to the horizontal is 75 degrees. To do this with the parallelogram method, I'm just going to use these as two sides for the parallelogram and then draw in the other two sides. My resultant is the diagonal of the parallelogram that starts at the same point that my original two vectors started. So it's the diagonal going this way across the parallelogram. That's my u plus v vector. Now what I want to do is find the magnitude and the direction angle. I can start by finding the magnitude. That would be the length of this line segment. Now a couple of things about parallelograms that it's useful to know. One is that adjacent angles of a parallelogram are supplementary. So if we could find this angle of the parallelogram, then the angle here would be its supplement. And actually we could find that angle because we know the entire angle from the horizontal up to here is 75 degrees. The angle from the horizontal to here is 15 degrees. So if we just take 75 minus 15 degrees, that's going to give us that angle of the parallelogram. So this angle right here is 60 degrees. That means that the adjacent angle in the parallelogram is going to be the supplement to this one. That's 180 minus 60, so that's going to be 120 degrees. The other thing with parallelograms is that opposite sides are congruent. If this side over here is 4, that means that this side is also 4. Then if we look at what we've got, we're trying to find the length of this diagonal. We've got two sides and the angle between them. That means we can use the law of cosines. And I'm going to call this length x just to make this easier. We want to find x, so we're going to use the form of the law of cosines that has the x squared by itself on one side. That means on the other side we're going to have the other two sides squared, and then minus the product of those two times the cosine of the angle, which is 120 degrees. If we square these two and then add them together, we get 25. This is 24. And it happens that the cosine of 120 degrees is negative 1/2. That means we get x squared equals 37. So the x, or the magnitude of our resultant vector, is going to be the square root of 37. We've got the magnitude. Now we want to find the direction angle. That would be from the horizontal up to here. So what we really need to find is this angle from here to here. Once we find that one, then we can add the 15 degrees to it, and then we've got that all the way down to the horizontal. So we're trying to find this angle theta right here. Now we've got the length of this side, and we know this angle across from it. Now we can use the law of sines. So we have the square root of 37 over the sine of 120. And then we want to find the theta, so we're going to do this side over the sine of this angle. We'd have 4 over the sine of theta. First we're going to solve this for the sine of theta. That would give us 4 times the sine of 120 degrees divided by the square root of 37. Once we have that, then we're going to do the inverse sine to find our angle theta. It turns out that theta is approximately 34.7 degrees. And now for the direction angle for our resultant vector, we're going to take that angle plus the 15 degrees. So our direction angle for u plus v is going to be 34.7 plus 15 degrees, and that gives us 49.7 degrees.